Hello, college algebra enthusiasts. So today, right now in this session, we will talk about some basic exponential logarithmic models and how to use exponential functions and logarithmic functions to solve some of these problems. So one of the this exponential functions and the logarithmic functions are very much used in population dynamics. It's very much used in population dynamics and even 4 and 6 and other applications. But we're going to take a look at two main problems that arises usually in population dynamics. One is the exponential growth, and the other one is the exponential decay. So how do we do that? So this formula right here, a is equal to a naught e to the kt, right? That has an exponential function, and that represents the exponential growth of any population and various other entities. So for our purposes, let's just say it's a population, including, for example, this also can be used in finances and also in the compounding growth and things like that. Here in the exponential growth, this k. So you see you have a term a and you have a sub 0, an exponential function e, and then you have a k and a t, right? You have a k and a t. So if you rewrite this, so usually you have something like this. A is equal to a sub 0 or a naught e to the kt. So what are these various quantities? What is your a? What is the a sub 0? What is the k and what is the t? So a is amount, whatever that is. If it's a population, the amount of population. If it's a money, it's the amount of money, and so on. So it's usually amount at t, at any time t, right? That is your a. This right here. This right here is your a. And the a sub 0 or a naught is the initial amount or initial population, right? Initial amount or initial population. In generally, the a at time t is equal to 0, right? Time t is equal to t naught, or sometimes you might say t is equal to 0, that initial amount. This k right here is the growth rate if it's the k is positive. It's a decay rate, right? Rate of decay if k is negative. So k depends on whether it is positive or negative. It is either, you can say it's a growth rate or decay rate. So this would be growth rate if k is positive, or decay rate if k is negative. And t is the time. So these are the main components of these exponential growth model. So let's take a look at this particular simple problem and see how do we solve these problems. In solving these problems, usually the way the strategy or the way that we solve them is the following. So usually you're going to have an equation that has an expression here, right? And then you may have an expression, let's just say expression number 2 times expression 2, right, times e to the something, right? You're going to have another something in here, right? So the way that you solve this, you isolate the e. So basically divide whatever you need to divide and so on. You isolate the e, and then you keep everything else in here. You keep everything else on the other side. And then what do? Then you take the logarithm on both sides. Since it's e, you take the natural logarithms on both sides. So then what's going to happen is that this side is going to stay as a logarithm of this, but this side is going to have just the exponents of that, right? Just this exponent of that is going to be here. And then now you have an expression, a logarithmic equation that you know how to solve. So that is the idea behind it. So again, the idea is isolate your e. So you're going to have some sort of an expression, isolate your e, and then take the natural logarithm both sides, and then solve the expression, right? So let me do an example, then you'll know what I'm trying to say. So let's take a look at this particular problem. In year 2004, somebody invested money in a savings account. The value of your investment t years after the 2004 is modeled by a, the amount equals 7600, right, times e to the 0.06t. It looks like a 6% growth rate, right? 0.068t. The question is, when will your account be worth $9,465, right? When will you have $9,465, assuming that your growth rate is, or the growth equation is, A is equal to 7600 e to the 0.068t. So let's see how do we solve this particular problem. So let's try to write down the equation that we have, and then we'll see what we need to do. So the given equation is A is equal to 7600, right? 7600 times e to the 0.068t, right? All right. Now, what I'm going to do, what I want is, I want this A to be $99,465, right? And again, I don't know what the T is. I don't know how long it's going to take, but I am going to use the logarithmic or exponential functions to solve that. So I know my amount that I'm looking for. This is the model that is given to me. So the only unknown in this particular equation is T, right? So my goal is to figure out that particular T. So how do we do that? So to do that, as I said earlier, here I have an exponential function. I'm going to isolate it. To isolate this, what I'm going to do, I'm going to divide both sides. I'm going to divide both sides by 7600. When I do that, then the left-hand side is going to be 9465 divided by 7600. And the right-hand side is going to be simply e to the 0.068t, right? So that's what I have. Now, what do I do? Now, as I said earlier, so now I kind of, have something like this, right? So I kind of isolated the E. I kind of isolated the E now. So the next step, I'm going to take logarithms, natural logarithms on both sides. If you recollect a long time ago, I said, I kind of jokingly said, Tennessee lobsters, right? What does that mean? Taking natural logarithms on both sides, right? So Tennessee lobsters, right? So that's what I'm going to do. I'm going to take the ln of 9465 over 7600 equals ln of e to the 0.068t. Right? When I do that, the right-hand side, since the natural logarithm and the exponents are the inverse of each other, right? That is going to go away. So I'm going to be left on my right-hand side with simply 0.068t. My left-hand side is going to be ln of 9465 over 7600. You can simplify this right now, or you can wait later. It doesn't matter for computational purposes. It really doesn't matter. So we'll work it out everything together. Again, my goal is to figure out the T, right? To isolate the T, what I'm going to do, I am going to divide both sides by 0.068. When I do that, my left-hand side is going to be ln of 9465 over 7600, and the whole thing is divided by 0.068. That should be equal to T right there. And that's what I have. And if I use the calculator, if I try to simplify this, the answer that I will have would be T is approximately, you're going to have 3.22724. So it will take 3 years, right? Almost like 3 years and quarter year. 3.25 years, almost like 3 years and 3 months, right? So it's going to take 3 years and 3 months for the money to become 9465, assuming that the growth rate is, or the growth model is A is equal to 7600 times e to the 0.0680. And that's how we solve this particular problem. Again, let me emphasize what I just did. I have this particular equation that is given to me as my growth model, and I plug in the given information. Now I have this expression right there. The only thing that I have is I need to isolate the E. To do that, I'm dividing or multiplying, whatever I need to do. I did that. Then again, I need to isolate my T. To do that, I took natural logarithms on both sides. When I did that, right hand side is simply becomes the exponent, which is 0.06t, and the right hand side has a logarithmic expression. Using the calculator, we can figure that out. And then to find the t, I'm dividing by 0.068. When I do that, my answer happens to be 3.22724. Approximately in years, that will be 3 years and close to 3 months. And that is the similar formula we are going to be using to solve this particular population dynamics as well, right? So let's see how do we do that. So let's try to understand what this problem is and try to model what we have, and then we'll just go from there. Again, the model that we are working on is a sub 0. A is equal to a sub 0 times e to the kt. A is the amount of population after time t. A sub 0 is the initial population. K is the growth rate, and t is the time, right? As we looked at it earlier. So let's see, what do we have here? So here, the information is given the population of Africa was 807 million, and by 2011, it had grown to 1052 million. All right. So initially the population was, that is a sub 0, is 1807 million. So let's say everything is million, right? So 807 million, right? And after 11 years, because it was 2011, right? By 2011 means it's 11 years. So e to the k times t is the 11, right? Time. It had grown to be 1052 million. So the equation that I have is 1052, the amount of population after 11 years, right? If the initial population is 807, and that's what I have. So why am I doing all this? The reason that I'm doing all this is to figure out my growth rate, right? Figure out my k. So I need that to solve what I'm going to do. So here I know my initial population. I know my population after 11 years. I know my initial population. I know the time. The only thing that I have, the only thing that I need to figure out and that I have in this particular equation is k. So let's see, how do we find that k? Again, we're going to use the same thing that we did earlier. I'm going to isolate the exponential function, keep everything else on the other side, and take the logarithm and then solve. So let's do that. All right, so to do that, I'm going to divide both sides by 807. When I do that, I'm going to have 1052 divided by 807 equals e to the 11 times k. That's what I have, right? Wonderful. Now, what I'm going to do, just to isolate the k, I'm going to take the natural logarithms on both sides. When I do that, I am going to have ln 1052 divided by 807 equals ln e to the 11 times k. And again, as I said earlier, the natural log and exponential functions are inverse of each other, so they'll get canceled out. So my right-hand side is going to be 11 times k, and the left-hand side is going to be ln of 1052 over 807. There is nothing wrong in computing right away, but I'm not going to do that. I'm going to do that in the next step. So how do I do that? So this tells me my 11k, ladies and gentlemen, 11k is equal to ln of 1052 divided by 807. And so therefore, k, the growth rate equals ln of 1052 divided by 807. And the whole thing is divided by 11. Use your calculator to figure out how much that is. I already computed that, and that k happens to be, if you use the calculator, it's 0.0241022, but I'm going to only take the 4 decimal places. I'm going to ignore them. I'm not going to bother about them. I'm just going to only take the 4 decimal places. So my k here, the growth rate for that particular population is 0.0241. All right, I got my k. Now, what am I going to do, right? So I'm going to use this. To figure out what I need to do. So what I'm supposed to do, the question is, when will the population be 2,000 million? The question is, when will the population be 2,000 million? So the question is, when the A, what time, after what time, after how long A is going to be 2000, if the initial population is 807 and the growth rate K happens to be 0.0241 times T. Again, here the unknown is T. I don't know how long it's going to take to get to 2000, but I have a nice equation with the only one unknown, and that unknown is T, right? So let's see how do we find that T. We're going to use the same thing that we did earlier. So to make my life easy, let me move a few things here and there. So let me move this over here and then move this up there and shrink it. All right, so when we do that, let's see. So now I can move this up here. So the same technique that we're going to do there. So I'm going to isolate the E. To do that, I'm going to divide both sides by 807. If I do that, you would agree with me, I'm going to have 2000 over 807 equals e to the 0.024t, right? Now, to isolate the t, I'm going to take the natural logarithms on both sides. When I do that, the left-hand side is going to be ln of 2000 over 807 equals ln of e to the 0.024t. And again, as I said earlier, ln and e are inverse of each other, so they kind of go away. What I'm going to have on my right-hand side is I'm going to have simply 0.24t, and the right-hand side is going to be ln of 2000 over 807. Now, if I try to solve, let me move these things in here, I have some space. Somehow the line crossing the T has been cut off. Let's rewrite it. All right, so what I have here is, let me do that. So if we solve that, so what I'm going to have here is the following. So then therefore, from here, if I want to solve for t, I think I missed one over there. I think you're supposed to keep the one all over the place. So let me keep the one here, one here, one here, and one here. So therefore, then t would be, I'm going to divide both sides by 0.0241, 0.0241. Then t would be ln of 2000 over 807. For some reason, I wrote it as t. And the whole thing is divided by 0.0241. When you do that, the t is approximately how much? The t is approximately 37.6589. So you can just say, approximately 37.66. So it will take 37.66 years for the population to reach 2000 million. In other words, 2 billion, right? For the population to reach 2 billion for that particular model, it will take 37 years, 37.66 years. All right. So that is how we would solve this problem. So the answer here, this would be this right there. All right, so let's try to take a look at the following. So this is called the half-life, right? How do we measure the half-life? So if you read the book, if you remember, the fact is, the scientific fact is the following. It takes 5,715 years, 5,715 years, right? For the amount of carbon-14, to become half, to decay into half, right? To decay into half. And this is called the half-life period, right? This is called the half-life period. So, and we're going to use this. So if you have any object, every object has some sort of a carbon, right? So based on the amount of carbon that it has, we can figure out how long what is the age, or how long it's been there. We can figure those things out if you know the initial carbon 14 amount, right? So for that, there's a nice equation in your book on page 497. I'll let you do that. If you try to model this decay model, we are going to have A is equal to A sub 0 e to the kt. Remember, it's a decay model because the carbon dating is kind of like a going down, right? It's going down. Let's just say if this is initially A, and that's your A, right? And this looks like a half. This right here, the time that it takes to reach that is 5,715 years, right? That is the model. And the time that it takes, if you have a model like this, right? The the amount of carbon 14, right? If this is the initial, this is going to be A over 2. The amount of carbon for it to become half, it'll take 5,715 years, right? So, and when you try to model this, so basically, if you want to have A sub 0, A to be A sub 0 over 2, half of the original and the initial amount of carbon, if you want to, we know that it takes 5,715 years, right? We can figure out the growth rate, and there is a problem in your book. You can do that, and when you do all that, that decay rate, right? In other words, negative growth rate happens to be the following: negative 0.0000121. So we're going to use that as in our model. So in other words, for this problem number 3 and 4, or any aging problem, what we are going to use is we're going to use this particular equation, that is A equals A sub 0, the initial amount, times e to the negative 0.0000121 times t. And that is what we're going to use, right? So let's use this particular equation to solve this particular problem. So it says the half-life of lead is 22 years, right? Half-life of lead is 22 years. How long it will take for a sample, right? How long it will take for us? It will take for a sample of this substance to decay into 80% of the original amount. All right, so let's try to do this problem, right? The half-life of lead. This is different than the carbon 14, correct? So this whatever that we have here is for the carbon 14. So we cannot use this one. We're going to keep it back right there. So for this problem, the half-life of lead is 22 years. So which means whatever the initial amount is, if its initial amount is A sub 0, right? For it to become half, A sub 0 over 2, right? I don't know the growth rate is, it's going to take 22 years. That's the half-life of a lead, right? That's what the half-life of lead. Let's use that to figure out the same way that we were earlier, figure out the K. Once we figure out the K, then we can figure out how long it will take for the substance, for a sample of this substance to decay to 80%. We can figure that out. So first we need to figure out the K, the decay rate for this particular lead. Let's do that. So here's the equation that we have. We set it up. Let's try to solve this for a K. Since A naught and A naught here both are same, I can divide this, right? So if I divide by A sub 0 on both sides, I am going to have this following equation, which is 1/2 equals e to the 22k, right? And then again, I have to solve for the k. To do that, what I'm going to, just like we did earlier, I'm going to take the ln on both sides. I have ln of 2 equals ln of e to the 22k. And this tells me 22k equals ln of 1/2. And so therefore, the growth rate or the decay rate in this case is k equals ln of 1/2 over 22. And now if you use the calculator to figure out what that is, you're going to get, negative 0.0315067. I think we'll just keep the 4 decimal places. So we'll just keep the spot and we can ignore the other, right? We don't need to worry about these parts. We'll just keep those numbers. So that's the decay rate. We will use that to see how long it takes for it to decay to 80%, right? So let's do that. So before I do that, let me just move this down here. This is the, we don't really need this, by the way. We only need this for this one. So let's see. Wonderful. So now we have the, for this particular lead, we have the equation. That equation is the following. That is A, the amount of lead equals A sub, A sub 0, the initial amount, times E to the negative 0.0315t, right? And we're going to use that to figure out the next problem. So the sample has 80% of the original, right? The amount that we have is 80% of the initial amount, 80% of A sub 0, which is same as saying 0.8 times the A sub 0. So the amount is 0.8 times A sub 0.8 times A sub 0. And so therefore the equation that we have is the if it's decayed into 80%, which means that amount that is left is 0.8 times A sub 0, whatever the initial amount is, we don't know, times equals A sub 0, the initial amount, times E to the negative 0.0315t. So we are looking for the time. We are looking for the time t, so that the amount has been decayed into 80%, or after that it decayed into 80%. So how do we do that? Same like just we did earlier. I'm going to divide both sides of the equation by A sub 0. When I do that, this equation turns into 0.8 on one side. The other side is going to be E to the negative 0.0315t. Then again, just like our goal is to figure out the t, to do that, I'm going to do the ln on both sides. When I do that, I'm going to have a ln of 0.8 equals ln of E to the negative 0.0315t. And as I have been doing this all along, that's going to go away. So my right hand side is going to be negative 0.0315t, and the left hand side is going to be ln of 0.8. And so therefore, if I try to solve this for t is going to be ln of 0.8, and the whole thing is divided by the coefficient of t on the other side, which is negative 0.0315. And if you try to plug this into a calculator, you're going to get approximately t as the following. So you get 7.08392, right? You're using a logarithmic calculator, which will be 7.08392. And that's the answer for this particular problem right there. All right, so let's take a look at the next problem. The next problem is carbon 14. We already solved this, by the way. So we already solved this problem for the amount of carbon dating. Again, you can find this on page number 497 of your book, right? So let's see, how do we solve this problem? Again, as I said earlier, it takes 5,715 years for carbon 14 to become half, right? Half of what it was originally. And so if you do that by the same way we did earlier, the growth rate, or in this case, the decay rate, is going to be negative 0.000121. So therefore, the equation that we're going to work through is A is equal to A sub 0 e to the 0.00000000121t. So we're going to use that to do that. So let's see what do we need to do here. So skeletons were found at a construction site in San Francisco in 1989. These skeletons contains 88%. It contained 88% of the expected amount of carbon 14 found in a living person in 1989 how old were these skeletons, right? How old were those skeletons? So how do we do that? So the amount of skeleton happens to be 0.88. So whatever the initially is going to be 88%, which is 0.88 times a sub 0 equals, again, I'm just borrowing the equation from here, right? Borrowing the equation from there. That is going to be 0.88 equals a sub 0 e to the negative 0.000121t, right? That's what we are doing. And now again, we're going to use the same thing that we did earlier before. I'm going to divide both sides of the equation by a sub 0. When I do that, my left-hand side is going to be simply 0.88, and the right-hand side is going to be e to the negative 0.000121t. And I'm going to take the logarithm on both sides to simplify for t. When I do that, my left-hand side is ln of 0.88, and the right-hand side is ln of e to the negative 0.000121t. And as we have been doing earlier, ln and exponential functions are inverse of each other, so they cancel out. So my right-hand side is going to be simply negative 0.000121t equals ln of 0.88 divided by ln of 0.8. So if I want to solve for t, I'm going to divide both sides by negative 0.000121. When I do that, the left-hand side becomes ln of 0.88 over negative 0.000121. And if you simplify, your t would be 1056 point, I believe, 1056.47. And again, for those who are wondering, how come, I have a negative in here, this is positive, right? How come I have a negative on the bottom, this is positive? The reason because ln of 0.88 is going to be a negative as well. So the negative and negative will get canceled. So you will have a positive number. So in other words, those skeletons were 1,056 years old, 1,056 and a half years old. So we can conclude this kind of aging, this kind of forensics, we can do that, or anthropology, right? So we can do all that using mathematics, and that's what they have been. That's what they are doing with the mathematics. All right, I will stop it right here. In the next video, we will take a look at the logistic growth model. So, and again, in particular, we will take a look at the modeling of the spread of the flu, especially we're talking about the spread of the coronavirus. I think I'm going to do this problem. So if you really see, the original problem is something like this, which has a similar model. But I think since we are dealing with the coronavirus, it might be of the best interest to look at some mathematical models that deals with these kind of models, and then you'll understand better when scientists say, what do we mean by the spread, what is the projections, and so on. You can have a better idea. So we're going to do this problem in the next video. I will stop it right here. I will see you all later.